Welcome! This is a live tutorial on a real Jetson AGX Thor developer kit. Not a recording, not a simulation. Every state change, reboot, and cryptographic check happens on the developer kit in front of us. On the right, a live inference pipeline runs on the GPU, shown at key points in the tutorial to demonstrate real work happening on the hardware, while we manipulate its boot and identity. The inference pipeline uses DeepStream and TensorRT with the PeopleNet Transformers model to do live detection of people, faces, and bags on a video feed of a crowd of people. To start, we walk through some background on Orca OS, the boot chain, key management, on-target updates, so the active steps later make sense. Then, 4 hands-on operations. First, provision. A trusted application on the device generates device-specific keys, giving this browser a way to verify it's talking to this exact device. Second, install a production update onto the inactive boot slot. The device reboots into it. Third, access production through a session authenticated on both ends, by something only the device can produce and only this browser can produce. And fourth, roll back to provisioning, the safe recovery path from a failed production update. The badge in the top header shows the current mode and slot. The connected indicator means the backend application is active on the device. The verified line tells you whether the cryptographic flow is live. Orca OS is Konsulko Group's production-grade embedded Linux distribution for Edge AI on NVIDIA Jetson. It's built on the Yocto project and ship-signed boot, an integrity-verified root file system, hardware-bound key management, atomic over-the-air updates, and a hardened production runtime, all reproducible from source. The foundation is Yocto Project 6.0, codenamed Rhinos, with NVIDIA's Jetpack 7.2 BS-P8 layered on top. The hardware under this tutorial is the Jetson AGX Thor developer kit, ARM Neoverse cores, and a Blackwell-class GPU. The user space stack includes systemd, ROC for over-the-air updates, CUDA, the DeepStream pipeline, the Docker container runtime, and PKCS11 tools for cryptographic operations and opt. We will cover 5 topics in this tutorial. Hybrid boot mode, how Orca OS demonstrates the security stack on unfused hardware. Secure boot, the chain of trust from silicon to file system mount, with each layer verifying the next. Key management, trust zone-based opt for both the boot path and applications with hardware-bound keys. On-target updates, the AB atomic model, signed bundles, and safe rollback. And production mode, the operational hardening that sits on top of the cryptographic foundations. Fusing a Tegra is permanent. Once the SBK and PKC fuses are programmed, the device can't be refused and cannot boot unsigned images. Hybrid mode is Konsulko's configuration for running as much of the production security stack as possible without committing the fuses on a Jetson platform. This allows engineers to validate a portion of the chain of trust without permanently modifying their hardware. From UFI down, the entire chain of trust is intact. UFI Secure Boot is enrolled with its own keys: platform key, key exchange key, and signature database, and verifies the signed kernel, DTB, and init RAM file system at every boot. DM Verity authenticates every root file system block against an embedded hash tree. DM Crypt encrypts the root file system at rest with a key derived from opt, and opt itself runs a full trusted execution environment in the secure world, providing device identity, LUX derivation, and the PKCS11 interface. What hybrid mode can't reproduce is the very early hardware verification chain, boot ROM to MB1 to MB2 to UFI. That chain depends on the PKC fuse being burned, because PSC ROM uses that fuse value to verify each of the bootloaders. On unfused hardware, bootloader verification is not performed. Now let's walk through the secure boot chain of trust on an Orca OS Jetson platform. The root of trust begins in the boot ROM and PSC ROM, fixed in the SCOC silicon. The PSC ROM uses the PKC hash from one-time programmable fuses to authenticate the next stage firmware. MB1 is the first piece of software to run on the BPMP. It is signed with the PKC key and authenticated by the PSC ROM. MB2 is the first bootloader to run on the CC Plex. It is PKC signed and authenticated by the PSC ROM. MB2 launches OpT and UFI. UFI is the industry-standard firmware interface, loaded from QSpyFlash and authenticated by the PSC ROM. It holds the secure boot key database, platform key, key exchange key, and signature database. The L4T launcher is NVIDIA's EFI application that selects which OS slot to boot. UFI verifies its PE signature against the secure boot database before executing it. The Linux kernel and init RAM file system are bundled in a boot image. The boot image and kernel DTB are loaded from the active kernel and DTB partitions. Both are PE signed and verified by UFI. The init RAM file system derives the disk encryption passphrase by calling OpT's LUX server trusted application, then opens the root file system and data volumes with LUX2. It then uses dmverity to authenticate the root file system before it's mounted. The root file system mounts read-only on the decrypted integrity-verified device. dmverity detects tampering at read time. The data partition mounts read-write, with LUX2 encryption protecting user and application data at rest. At this point, the chain of trust is complete. Now let's walk through NVMe disk partitioning on Orca OS. There are two kernel partitions, one per slot. They are in Android boot image format, and each image holds both the kernel and init RAM file system. The L4T launcher loads from the active slot. The inactive one is staged for the next image. There are two device tree partitions, one per slot. The device tree describes the hardware the kernel needs at boot. It's signed alongside the kernel, so kernel and device tree are verified together as one unit. Two 64-megabyte ESP partitions hold UFI's resources. These include the L4T launcher and boot configuration. The alternate is a fail-safe. If the primary can't be read, the firmware boots from the spare. App partitions hold the Linux root file system, one per slot. In this tutorial, they're 32 gigabytes each. The size depends on the production system build. Each is ext4 wrapped in dmverity for integrity and dmcrypt for at-rest encryption. UDA, user data. A single partition shared between slots, growing to fill the rest of the NVMe. It holds provisioned credentials, OpT secure storage, Rauch data, logs, and config. It is dmcrypt encrypted at rest with a device-specific derived key. In Orca OS, private keys are never stored in plain text on disk. Instead, keys are fused into silicon, enrolled in UFI variables, or held inside OpT. 3 families of keys, each with a different protective mechanism. The root of trust starts in hardware with fused one-time programmable keys. The PKC key pair verifies signed early boot firmware. The public key hash is burned into hardware fuses. The SBK, a 256-bit symmetric key, is optionally used to encrypt firmware payloads. UFI's secure boot uses its own X509 certificate chain, platform key, key exchange key, and signature database. They're an independent set of certificates, generated at build time and enrolled into UFI's authenticated variables. The DB certificate verifies the signed kernel, DTB, and init RAM file system at every boot. Trust Zone is an ARM CPU feature that splits the processor into the normal world, where Linux runs, and the secure world, where OpT runs. The split is enforced by the CPU itself, not by software, so even a fully compromised Linux kernel cannot read the secure world memory or extract keys held there. Trusted applications run inside OpT and provide services to the normal world. This build uses two: the LUX server trusted application and the PKCS11 trusted application. At every boot, the init RAM file system uses the NV-LUX server app to call Opti's LUX server trusted application. The trusted application combines its SIM2 key with this device's Silicon ECID using a NIST SP800 108 key derivation function to produce a LUX2 passphrase that is unique to this device. The passphrase unlocks the encrypted root file system and data volumes, then is discarded. The SIM2 key never leaves the secure world. The PKCS11 trusted application exposes the standard key generation, signing, verification, and encryption APIs to applications running in the normal world. Key material never crosses the boundary, only the operation result. Opti stores PKCS11 token state and any other persistent, trusted application data as encrypted blobs. The encryption key is a trusted storage key, TSK, derived inside Opti from the SoC's hardware unique key, a per-die secret fused at manufacture. The TSK is the basis for all secure storage and PKCS11 token operations. A blob copied off this device can't be decrypted anywhere else. This build uses REEFS, the rich execution environment file system, where the blobs live on the normal Linux file system. REEFS gives strong confidentiality and integrity. The trusted application encrypts and signs every object before handing it to the normal world supplicant for writing. A normal world attacker sees ciphertext only, but REEFS cannot detect replay attacks. RPMB, Replay Protected Memory Block, closes that gap. It's a hardware-rooted feature of modern storage controllers. A dedicated partition with a write counter, the storage chip itself increments on every authenticated write. The trusted application writes a monotonic sequence number alongside each object. Any attempt to restore an older blob fails the countercheck inside the secure world. The Orca OS root file system is protected by two kernel device mapper targets, DM-Verity for integrity and DM-Crypt for encryption at rest. Both are active on every boot and on every read. The read-write data volume is also protected by DM-Crypt. DM-Verity sits between the file system and the NVMe, invisible to user space. At image build time, a Merkle hash tree is computed over every 4 kilobyte root file system block. The root hash is embedded in the signed kernel command line, so it inherits the kernel's UEFI secure boot signature. On every read, the kernel verifies the block against the tree. A tampered block, even 1 bit, fails the check. The target returns an I/O error or panics the kernel. DM-Crypt sits underneath DM-Verity and encrypts the volume with AES-XTS 256. The volume is formatted as LUX2. At every boot, init RAM file system asks Opti for the LUX2 passphrase, derived per device as we saw earlier, then discards it once the volume is unlocked. Together, the two targets cover two distinct threats. DM-Verity defends against an attacker who writes to the NVMe. Modify a binary, put the drive back. The hash check catches it on the next read. DM-Crypt defends against an attacker who reads the NVMe. Clone the drive and inspect it. The LUX passphrase is derived using this device's unique ECID, so on any other system the derivation yields a different passphrase and the ciphertext is unreadable. Before this device can be promoted to production, we provision it. Provisioning is a one-time handshake where the device and this browser bind themselves to each other cryptographically. Both sides end up holding a private key, and both sides remember the other's public key. 4 things happen in sequence. First, on the device side, the PKCS11 trusted application generates a fresh key pair inside the secure world. The private half stays inside the trusted application. It can never be read out, even by root in the normal world. The public half is exported for this browser. Second, on the browser side, this page generates its own key pair in JavaScript and persists it in indexed DB, a per-origin store that survives across page reloads. Third, the device mints a signed cookie using its trusted application resident key and sets it in this browser. And fourth, both sides record the other's public key. The device stores the browser's pub key, and the browser stores the fingerprint of the device's pub key. Once we enter production mode, every API request between this browser and this device must satisfy two independent cryptographic factors: a valid cookie signed by the device and a per-request signature from the browser. A stolen cookie alone cannot impersonate this browser. The attacker doesn't have the browser-side private key. A different device pointing at the same browser can't impersonate this device. The public key anchor catches the mismatch on the very first request. Provisioning is complete. The device and this browser have exchanged public keys and the device-signed cookie is set. Look at the header. The fingerprint indicator now shows this device's public key fingerprint, confirming the device is provisioned. Rauch, Robust Auto Update Controller, is a mature open-source A/B update framework. Orca OS uses it to install signed update bundles atomically. Either the new system boots successfully or the old one is still there to fall back to. A Rauch bundle is an artifact containing all the data needed to update a set of slots with new software. Every bundle is signed. The signature and per-artifact checksums are verified before any byte is written, and a tampered bundle is rejected outright. The disk has 3 slot pairs: kernel, DTB, and root file system. One slot is active and running, the other is inactive. Rauch writes the new image into the inactive slot, then asks the bootloader to mark it as the next boot slot. The data partition is shared between slots and untouched by Rauch, so credentials, configuration, and logs all survive every update. On reboot, the new image comes up, and the bootloader marks the attempt as trying until a user space verifier confirms it's healthy. If that confirmation never arrives, the bootloader falls back to the previous slot on the next reboot. Rollback uses the same machinery in reverse. Mark the current slot bad, flip the active slot pointer, reboot, and the previous image is running again, untouched. Rauch will verify the signed production bundle, embed it in the provisioning image at build time, install the new kernel, DTB, and root file system into slot B, and mark slot B for the next boot. The device reboots into the production image. UEFI and Linux are locked down. These will be explained after the software update completes. The only remaining attack surface will then be the dashboard application itself. The provisioning cookie is signed by the opt resident device key. It survives the reboot like any session cookie. The device public key needed to verify it lives on the UDA partition, shared between slots, so the production image picks it up unchanged. The browser key pair is stored in browser local storage. The banner shows provisioning and slot A. After the reboot, it will say production and slot B. Click Apply Production Update to start the update process. Now let's quickly skip through the production software install and reboot process. The Rauch update completed successfully. The signed production bundle was written to slot B, marked as next boot, and the system rebooted. We're now talking to the hardened production image across the authenticated connection. Look at the header. It now shows verified, indicating that the connection to the device is authenticated with the provisioned key pair. 3 attacks are now blocked: cookie theft, device swap, and second browser takeover. An operator with physical access to a production device can no longer reach the firmware the way a developer would. The interactive UEFI shell is disabled in the build. The setup menu is disabled, and the USB boot path has been removed from the platform's boot order. The only thing the device can boot is the signed kernel image on NVMe. If that image fails to verify, the boot halts. We disable these interfaces to provide defense in depth and reduce the attack surface. With these paths closed, an attacker is unable to gain any additional information about the system or modify boot parameters. As a quick challenge, if a serial console is connected to the device, review the boot logs to confirm that UEFI no longer offers the option to break into the menu. Both interactive login paths are disabled in production. The Orca user is locked on the serial console and OpenSSH isn't built into the root file system. Port 22 doesn't listen. Only the dashboard on port 80 responds. We remove these interfaces to provide defense in depth and reduce the attack surface. The only remaining attack surface is the tutorial dashboard, listening on port 80 authenticated by the two-factor cryptographic flow set up at provisioning. 2 quick challenges. First, if a serial console is attached to the device, try logging in with the Orca user and the documented password. The prompt will reject the attempt because the account is locked in production. Second, try logging in over SSH using the supplied SSH keys. Port 22 isn't even listening because OpenSSH isn't built into the production root file system. Every API request is gated by 2 cryptographic factors, one held by the device, one held by this browser. The device signs a session cookie with a key sealed inside opT. The browser verifies every cookie on every state poll. This browser also holds its own key pair, generated at provisioning. Every request is signed by this browser before it reaches the device. 3 attacks are ruled out by these factors plus the mutual binding set up at provisioning. Cookie theft alone fails. The request still needs the browser's signature. A device swap is caught because the browser anchored the device's public key fingerprint on first contact. The mismatch fails on the very first state load. And a second browser trying to claim the device is refused because the device remembers this browser. A quick challenge: open an incognito or private window in Chrome or Firefox and try to connect to this device. The dashboard will refuse but a fresh session has neither the device-signed cookie nor the browser-side signing key, and any attempt to repair from the new browser hits the paired-only guard with an HTTP 409 conflict. That's the full Orca OS tutorial. You provisioned this device with a hardware-bound identity, installed an on-target production update to the inactive boot slot, watched the device reboot into the production image, and verified that every subsequent request between this browser and the device is cryptographically authenticated on both sides. From here, you can use the rollback button to return the device to the provisioning image and run the walkthrough again. It's the inverse of the production update we ran earlier. Rauch marks the current slot bad, the bootloader switches back to slot A, and the device reboots. This is the same recovery path the bootloader would take automatically if a production update had failed to boot, only this time it's manual. For more about Konsulko Group, our work on Orca OS for Jetson, our partnership with NVIDIA, or about Jetpack and Jetson Thor, the links on the page are the place to start. Reach out via the contact page. We work with Jetson customers from bring up through production.